Hello students, welcome to lecture 10 of atomic structure. The topic is quantum mechanical model of atom and Schrodinger wave equation. So, the classical mechanics deals with the motion of macroscopic objects. The classical mechanics deals with the motion of macroscopic objects. So the classical mechanics deals with the motion of macroscopic objects on the basis of Newton's law, and quantum mechanics deals with the motion of microscopic objects like electrons, atoms, and the quantum mechanics deals with the motion of microscopic objects like electrons, atoms, and molecules. So these are the microscopic objects. And the classical mechanics fails when applied to the microscopic objects. The classical mechanics fails when applied to microscopic objects like electrons, atoms, because classical mechanics ignored the dual behavior concept. This classical mechanics ignored the dual behavior concept. The dual behavior matter is called quantum mechanics. The dual behavior of matter is called quantum mechanics. And quantum mechanics developed in 1926 by Heisenberg and Erwin Schrodinger. And all the information about electron in atom is in orbital wave function psi, and Schrodinger wave equation is applied to electron in atom. It describes the stationary wave. So the Schrodinger wave equation is dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into E minus V into psi is equal to 0. So this is the Schrodinger wave equation. So here, or we can write h cap psi is equal to E psi. So here h cap is equal to minus h square by 8 pi square m into dou square by dou x square plus dou square by dou y square plus dou square by dou z square plus v. Here in these equations, psi is the wave function and m is the mass of electron and E is the total energy of electron and V is the potential energy of electron and E minus V is the kinetic energy of electron and H is the Planck's constant and XYZ, that XYZ are Cartesian coordinates in 3D space and H cap is the Hamiltonian operator. This is the total energy of a system. And let us discuss that significance of psi and significance of psi square. So this is the wave. Above the axis the value is positive and below that axis the value is negative, and at crossing the axis the value is 0. So the significance of psi and the significance of psi square. So the psi is a orbital wave function. It is a orbital wave function and psi square is a probability function. And psi gives the amplitude of electron wave. And psi square is always positive. Psi square is always positive. And psi is positive above the axis and negative below the axis and 0 at crossing the axis. And psi square describe the probability of finding electron. That psi square describe the probability of finding the electron. And where psi square is maximum is called orbital. Where psi square is maximum is called orbital. So this is the difference between the significance of psi and significance of psi square. So this is about quantum mechanical model of atom and Schrodinger wave equation. Next one, quantum numbers. Quantum numbers gives the complete information about the all electrons in atom, and these quantum numbers are 4 types. They are principal quantum number, number 2 azimuthal quantum number or subsidiary quantum number or angular momentum quantum number, and number 3 magnetic quantum number or orientation quantum number, and number 4 spin quantum number. So these 4 are quantum numbers. Let us discuss the first one, principal quantum number, and it is represented by n. And this principal quantum number proposed by Niels Bohr, and it is denoted by small n. and it denotes the size of the atoms. It denotes the size of the atom, and it gives information about orbit or shell. The orbit or shells are 1, 2, 3, 4, 5 and so on, or K, L, M, N and so on. And the maximum electrons present in any shell or orbit is given by 2n square. The maximum electrons present in any shell or orbit is given by 2n square. Here n is equal to first shell or second shell or third shell. For example, I am taking second shell. In that second shell, the maximum number of electrons given by 2n square is equal to 2 into n is equal to 2 because second shell. So this is the nucleus, first shell and second shell. In first shell we have 1s, and in second shell we have 2s and 2p. So n is equal to 2. So here 2 square is equal to 2 into 4 is equal to 8. So the maximum number of electrons present in second shell are 8. So here 2 electrons in 2s and 6 electrons in 2p. 2s2, 2p6, 2 plus 6, 8 electrons. So the maximum number of electrons present in any shell or orbit is given by 2n square, and it determines energy, velocity, radius of orbit in atom of hydrogen or hydrogen-like species. So it determines energy, velocity, radius of orbit in atom of hydrogen or hydrogen-like species. For energy, En is equal to minus 13.6 Z square divided by N square, electron volts by atom. And for velocity, Vn is equal to 2.18 into 10 to the power of 6 Z by N meter per second. And for radius, or N is equal to 0.53 N square by Z angstroms. And here Z is equal to atomic number. Z is equal to atomic number, and N is equal to orbit number or shell number. And it determines the angular momentum of electron present in orbit or shell. It is mvr is equal to nh by 2 pi. So here n is equal to 1, 2, 3 and so on. It determines the angular momentum of electron present in the orbit. Let us find that angular momentum of electron present in first shell is equal to, for first shell n is equal to 1, mvr is equal to 1h by 2 pi, and angular momentum of electron which is present in second shell, mvr is equal to, here n is equal to 2, so 2h by 2 pi, 2 cancel, h by pi. And electron present in third shell, that electron angular momentum mvr is equal to, n is equal to 3, so 3h by 2 pi. So this is the principal quantum number. Next, second one, azimuthal quantum number or subsidiary quantum number or angular momentum quantum number. It is represented by small l, and this quantum number proposed by Sommerfeld. And it denoted by small l, and the values of l are 0, 1, 2, 3 and so on up to n minus 1, and it determines the number of subshells or orbitals. The subshells are S, P, D, F, G and so on. So the values of L are 0, 1, 2, 3 and so on up to n minus 1, and it determines the number of subshells or orbitals. The subshells are S, P, D, F, G and so on, and it gives the information about shape of the subshells or orbitals. Shape of the subshell or orbital. So the s orbital shape is spherical, and p orbital shape is dumbbell, this is the dumbbell shape, and d orbital shape is double dumbbell, and this one is the double dumbbell, and f orbital shape is complex. So this azimuthal quantum number gives the information about the shape of the subshells or orbitals. S orbital shape is spherical, and p orbital shape is dumbbell, and d orbital shape is double dumbbell, and f orbital shape is complex. Here triple dumbbell, 1, 2, 3, and It expresses the energy of subshells, energy of subshells or orbitals. So s orbital having less energy than p orbital, and p orbital having less energy than d orbital, and then f and g and so on. So here this is the increasing order of energy. And the maximum number of electrons in a subshell is equal to 2 into 2l plus 1 or 4l plus 2. The maximum number of electrons present in subshell or orbital is equal to 2 into 2l plus 1 or 2 into 2 4 and 2 into 1 2. So 4l plus 2. Let me take some examples here. Here subshell or orbital, s orbital, p orbital, d orbital and f orbital. And here I am taking L values. S orbital L value 0 and p orbital L value 1, d orbital L value 2 and f orbital L value 3. So here I am taking subshell or orbital, and maximum number of electrons, and the formula 2 into 2l plus 1 or 4l plus 2. So the subshells are orbitals: s orbital, p orbital, d orbital and f orbital. And maximum number of electrons in s orbital 2, because here 2 into 2l plus 1 or 4l plus 2. So here 2 into 2 into L is equal to 0. The s orbital L value 0. So 0 plus 1 or 4 into L is equal to 0 plus 2. So here 2 into 0 0. So 0 into 2 0. So the maximum number of electrons present in s orbital 2. So let me take here s orbital 2 electrons. And in p orbital maximum number of electrons 6. Let me take this formula 4l plus 2. So here 4 into L is equal to 1. The p orbital L value is 1. So here 1 plus 2 is equal to 4 into 1 4 plus 2 6. So in p orbital the maximum number of electrons 6. 1 2 3 4 5 6. And in d orbital the maximum number of electrons 10. So here 4 into L value for d orbital 2. So 2 plus 2 is equal to 4 into 2 8 plus 2 10. So the maximum number of electrons present in d orbital is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And for f orbital, the maximum number of electrons 14. According to that formula, 4 into L value for f orbital 3 plus 2 is equal to 4 into 3 12 plus 2 14. So maximum number of electrons in f orbital 14, and it expresses the orbital angular momentum. Orbital angular momentum is equal to h by 2 pi into under root of L into L plus 1. Let me take that s orbital angular momentum. The SL value is 0. So h by 2 pi into under root of 0 into 0 plus 1, L into L plus 1. So it should be 0. The total value should be 0. So S is equal to 0. Means S orbital angular momentum 0 and P orbital angular momentum PL value is 1 and h by 2 pi into under root of L is equal to 1. So 1 into 1 plus 1. So 1 plus 1 2 into 1 2. So h by 2 pi under root of 2. So the p orbital angular momentum is h by 2 pi into under root of 2. And d orbital angular momentum, the dl value is 2 and h by 2 pi into under root of L is equal to 2. So 2 into 2 plus 1, 2 plus 1, 3 into 2, 6. So h by 2 pi into under root of 6. So the d orbital angular momentum h by 2 pi into under root of 6. So this is about azimuthal quantum number or subsidiary quantum number or angular momentum quantum number. It is represented by small l. Next, third one, magnetic quantum number, and it is represented by small m. And this magnetic quantum number proposed by Lande, and it is denoted by small m. And the values of ml varies from minus L to plus L, including 0. So the value of ml varies from minus L to plus L, including 0. I am taking here subshell and here orbitals and here ml values. So the subshell is s orbital and orbitals 1, the sublevels only 1, and that ml value is 1, that is 0, and the subshell p and the orbitals, the sublevels 3 p orbitals px, py, pz, and that ml values minus L2 plus L, including 0. So middle one 0 and right side plus 1 and left side minus 1. So minus 1 to plus 1 including 0. So total 3 orbitals. And d subshell orbitals 5. Let me take that orbitals 1 2 3 5. So middle one 0 and here plus 1 plus 2 minus 1 minus 2. So total orbitals 5 and that ml values minus L2 plus L including 0. So 0 minus L2 plus L. And subshell F and orbitals 7. These are the sublevels 7, 1, 2, 3, 4, 5, 7. Middle one 0 and plus 1 plus 2 plus 3 minus 1 minus 2 minus 3. So minus L2 plus L including 0 minus L2 plus L. So the value of ml varies from minus L2 plus L including 0. And the total number of orbitals present in a shell equal to n square. The total number of orbitals in a shell or orbit is equal to n square. Let me take the table here. Shell means orbit and number of orbitals n square. The shell 1 means first orbit. In first orbit the total number of orbitals only 1. In second orbit and third orbit, fourth and fifth. In second orbit or in second shell total number of orbitals 4. In third shell total number of orbitals 9. In fourth total number of orbitals 16. In fifth 25. Let me take one example here. I am going to find that total number of orbitals in third shell means third orbit. So here it is a nucleus, first orbit, second orbit and third orbit or third shell. This is the third shell. So in that third shell we have 3s orbital, 3p orbital and 3d orbital. 3s 1 orbital plus 3p, p orbitals 3, so plus 3 plus d orbitals 5, so plus 5 is equal to total 9. So according to that formula n square. So here n is equal to 3 because it is a third shell. N is equal to 3. So n is 3. So 3 square is equal to 3 3s are 9. So the total number of orbitals present in a shell is equal to n square. So here in this third shell 1 3s and 3p orbitals and 5 d orbitals. 1, 2, 3, 4, 5. So total 9 orbitals in third shell. And the number of orbitals present in a subshell is equal to 2l plus 1. The number of orbitals present in a subshell or orbital is equal to 2l plus 1. Let me take one table here. Subshell and number of orbitals. So the subshell is s orbital, and here p, d and f. So number of orbitals present in a subshell s. So the s L value is 0. So according to this formula, 2 into 0 plus 1 is equal. So according to this formula, 2 into s L value is 0. So into 0 plus 1 is equal to 1. So the total number of orbitals present in a subshell is 1. So here 1. P subshell. So total number of orbitals present in a p subshell according to this formula, 2 into the p L value is 1 plus 1 is equal to 3. So here number of orbitals in p subshell 3, and number of orbitals in d subshell according to this formula, 2 into L value for d is 2 plus 1 is equal to 5. 1, 2, 3, 4, 5. So total number of orbitals present in d subshell 5. And number of orbitals present in f subshell according to this formula, 2 into L value for f is 3 plus 1 is equal to 6 plus 1, 7. So here 7. So these are the subshells, and these are the total number of orbitals present in subshell. And it tells us about splitting of spectral lines in magnetic field called Zeeman effect. Splitting of spectral lines in magnetic field called Zeeman effect. It tells us about the splitting of spectral lines in magnetic field called Zeeman effect. And it tells us about orientation of orbitals in space. It tells us about orientation of orbital in the space, and it gives the information about degenerate orbitals. Degenerate orbitals. It gives the information about degenerate orbitals. Degenerate means the orbitals having same energy. For example, I am taking p orbital. It contains three orbitals, px, py, pz. These three orbitals having same energy, and d orbitals 5, dxy, dyz, dxz, dx square minus y square, and dz square. And f orbitals 7, 1, 2, 3, 4, 5, 6, 7. These 7 f orbitals having same energy, so these orbitals are called degenerate orbitals. And these 5d orbitals having same energy, then they are called degenerate orbitals, same as these 3 orbitals. This is about magnetic quantum number. Next, fourth one, spin quantum number. The spin quantum number represented by S, and it is proposed by Goldsmith and Uhlenbeck. The spin quantum number proposed by Goldsmith and Uhlenbeck, and the spin quantum number represented by S, and it represents the direction of electron spin around its own axis. So this is the electron own axis, and it represents the direction of electron spin around its own axis, either it clockwise direction or it anti-clockwise direction. And that ms values, if that electron spin is clockwise direction, then that ms value is plus of, it is a clockwise direction. And if electron spin is in anti-clockwise direction, the ms value is minus of anti-clockwise direction. And the total spin of atom is plus or minus of into n. So here n is equal to number of unpaired electrons. Let me take one example. Nitrogen atom total spin. We know that nitrogen atomic number 7 and electronic configuration 1s2, 2s2, 2p3. So in s orbital, in 1s orbital 2 electrons, in 2s orbital 2 electrons, in 2p orbitals 3 electrons, and these 3 are unpaired electrons. So here n is equal to 3. According to that formula, total spin is equal to plus or minus 1 by 2 into n. So here n is equal to 3. The unpaired electrons 3 into 3 is equal to 3 by 2 plus or minus 3 by 2. So total spin in nitrogen atom plus or minus 3 by 2. And spinning electron produce angular momentum equal to mu s is equal to h by 2 pi into underscore s into s plus 1. So spinning electron produce angular momentum equal to mu s is equal to h by 2 pi under root of s into s plus 1. So here h is equal to Planck's constant and s is equal to spin. So this is about spin quantum number. So 4 quantum numbers are over. Principal quantum number represented by small n, and azimuthal quantum number or subsidiary quantum number or angular momentum quantum number represented by small l, and magnetic quantum number or orientation quantum number represented by small m, and spin quantum number represented by s.